The next relation, the next kind of binary relation before us is antisymmetric relation. This is a special kind of relation, you see. Let R is a subset of A cross A. That is, R is a binary relation on an R-empty set A. Then R is antisymmetric if AB belongs to R and BA belongs to R, implies A is equal to B. You observe the definition. What is the case of symmetry? If A is related to B, then B must be related to A. What is antisymmetry? If at all you have two pairs such that AB belongs to R and BA belongs to R, then you must have A is equal to B. Yes. There are very few relations here. What are they? Let us study the nature of antisymmetric relations. Observe the relation is equal to an R. That is a special relation, of course, which is symmetric and antisymmetric. All I mean to say is, if x is equal to y, then automatically y is equal to x. So this is the symmetric character. Is equal to is symmetric. And x is equal to y, y is equal to x. If you take, automatically x is equal to y. So it is antisymmetric also. Of course, by looking at equal to y, equal to anywhere else, you may be, of course, got confused. Let us witness one more example. You consider the relation less than or equal to an R. If you have x less than or equal to y and y less than or equal to x at s time, then what can you say? X is equal to y. This is antisymmetric. Similarly, observe greater than or equal to an R, greater than or equal to on the set of real numbers. If you have A greater than or equal to B and B greater than or equal to A at once, then you can be in a position to say that A is equal to B, correct? So greater than or equal to is also antisymmetric. One more. Consider the relation subset of on power set of a set. If at all you have two sets, B subset of C and C subset of B at a time, what can you say? B is equal to C. B is related to C and C is related to B. You are able to have at once, then that implies B is equal to C. This is the nature of antisymmetry. One more thing is there. Where another example is a factor of on n. If you have two integers, two natural numbers, A and B, such that A is a factor of B and B is a factor of A, then I think you know this symbol. A is a factor of B, B is a factor of A. Both of these, if they happen simultaneously, then clearly you will be able to say that A is equal to B, provided both A and B are natural numbers. These are the famous antisymmetric relations. After noting down the characteristic features of equivalence relation, its meaning, its definition, and related examples, now we turn our head towards one more relation. Last but not least, it's a very good relation. It's also a famous relation. Let us have its name. Partial ordering relation. Pseudo ordering relation. Quasi ordering relation. Well, even though there are three names all these three names correspond to one particular relation, and the most general and famous name is a partial ordering relation. What do you mean by a partial ordering relation? And sometimes it will be abbreviated as a PO relation also. What do you mean by PO relation? Don't read it as PO relation. It is PO relation, that's all. What do you mean by PO relation? Partial ordering relation. Well, it is a time now for us to go through the meaning of, or rather the definition of a partial ordering relation. If R is a subset of A cross A, where A is a non-empty set, what can you say about this? R is a subset of A cross A. What is the meaning of that? R is a relation on A, binary relation on A. Then R is said to be a partial ordering relation on A if and only if, number one, R is reflexive. R is reflexive. Number two, R is antisymmetric. And number three, R is transitive. R is transitive. Yes. R is reflexive, R is antisymmetric, and R is transitive. If these three types of character are exhibited by a relation, then that particular relation is said to be a partial ordering relation or a pseudo ordering. Is here P is silent. Don't read it as pseudo. It is pseudo. Pseudo ordering relation, a quasi ordering relation. In whatever name you like to call, you can call. And of course, famously, it is read as partial ordering relation. And what is meant by a partial ordering relation? It should have three types of character. Number one, it's reflexive. Number two, it is antisymmetric. Number three, it is transitive. Yes, my dear friend, you might have observed one particular item here. Instead of antisymmetry, if symmetry is involved here, then it becomes an equivalence relation. So between equivalence relation and a partial ordering relation, there is a thin difference. What is that? About the second condition. If the second condition is symmetry, first and third remaining the same, is an equivalence relation. If the second condition is antisymmetry, first and third remaining the same, it is said to be a partial ordering relation. Yes. Well, let us now go through some examples of partial ordering relation. Observe the relations is equal to an R, less than or equal to an R, greater than or equal to an R, is a subset of on power set of A, is a superset of on power set of A, is a factor of on N. It is reflexive. X is equal to X. It is, the speciality is both an equivalence relation and a partial ordering relation, symmetric and antisymmetric. Of course, it is the unique relation at our disposal. There might be even more, but see, this is the unique relation before us at our disposal, which is both symmetric and antisymmetric. And surely it is transitive also. So it is both equivalence relation and partial ordering relation. Like here, reflexive because X less than or equal to X. Antisymmetric because X less than or equal to Y less than or equal to X implies X is equal to Y. Transitive x less than or equal to y less than or equal to z implies x less than or equal to z. Hence, it is a partial ordering relation. Actually speaking, this is of course called dual of this. If this is a partial ordering relation, its dual is also a partial ordering relation. Good then, subset of A is a subset of A for all A, reflexive. A subset of B subset of A. If you have both at once, then A is equal to B. Antisymmetric. What about transitivity? A is a subset of B is a subset of C, then A is a subset of C. Transitive. So, partial ordering relation, partial ordering relation, partial ordering relation. This is also, and this is again, is a factor of, it is again a partial ordering relation. Out of all these, this has the speciality. What is that speciality? Is both an equivalence relation and a partial ordering relation. That happened because it is both symmetric and antisymmetric. These are just PO relations. PO relation, PO relation, PO relation, PO relation, PO relation. That's it about partial ordering relations. Regarding relations, you cannot put a full stop, you can put a comma only. And these are enough, it seems, to face any type of question in the competitive examination. And besides the relations, there has been one more beautiful concept in sets, namely partition on a set. That also we may have to learn, because there has been a one-one correspondence between the number of partitions and the number of equivalence relations. For that reason, you have to know what is meant by a partition. The last but not the least, partition on a set. Let capital A be any non-empty set. If A1, A2, A3, etc., An are subsets of A such that number 1, AI intersection AJ is equal to phi. Number 2, union of all AI, I is equal to 1 to N is equal to A. Observe the definition. First of all, basically, what is a partition? It is a family of subsets. It is a collection of subsets of the main set. What type of subsets? Pairwise disjoint. If you take any two of them, that is joint. If you take any two of them, A1 intersection A2, phi, A2 intersection A3, phi, A1 intersection A3, phi, if you take any two distinct elements, they are absolutely disjoint. They will have no common elements at all. And the union of all those sets must be the entire set A. Well, let us have an example for the same. Please follow the definition carefully in your mind, and I like to remove it. Let us have an example of a partition so that you can understand the definition very carefully. Look at this. Let A is equal to 1, 2, 3, 4, 5, 6, stop. Write A1 is equal to singleton 1. A2 is equal to singleton 2, 3. So, set containing 2, 3. A3 is equal to 4, 5. A4 is equal to set containing 6 only. You observe the union of all this, you will be going to get A. You find the intersection of any two sets among these, empty. Therefore, A1, A2, A3, A4 set of subsets is a partition. Well, is it the only way to get it? To get a partition? No, not that. You can have so many partitions. So look here. 1, 2, 3, 4, 5, 6. Another partition. Like that, how many partitions you can have? It is a question of permutations and combinations, of course. And it's not impossible. You can easily get the number of partitions. The main thing here to be grasped is number of partitions on a finite set is equal to the number of equivalence relations on the set. That's it. In order to enjoy that concept only, we could have learnt about a partition. So, what is the thing to be written? We shall have it in the form of a sentence. This is a partition, this is also a partition, this is a partition. Well, the valuable sentence that must be grasped in your mind, that must be stored in our memory is this. Follow the sentence carefully. If A is a non-empty finite set, then the number of partitions on A is equal to the number of equivalence relations on A. This is the most valuable sentence that one must keep in mind. That's it. This is the essence of equivalence relations, of course. If a finite set has been given to you, and if you are asked to find the number of equivalence relations, then you find the number of partitions that can be formed on A. And it will be discussed while solving numerical problems. That's it.